great pleasure to have Sanjay Mangulam from the illustrious, fantastic Queen Mary College, University of London, who will be talking to us about counting and construction of D-brane quantum states.
Great, thank you. Thank you for the invitation to be here and to speak. Indeed, that's about counting and construction of D-brane quantum states. So in fact, I was asked a very pertinent question. Usually you construct first and then you count. So, but a lot of the time we encounter situations here in gauge string duality where it is easier to count, to know how many of something there are. And then you want to know, is there an algorithm from the counting to go to the construction? And we will see basically this question arising and some interesting answers to that. Okay, so the setup is string theory on AdS 5 cross S5 with the 5-form flux N, radius R, string coupling, dual to N equals 4 super Young-Mills with UN gauge group. So this rather remarkable duality involves a whole load of things in AdS 5 cross S5. You have the strings, the excitations, the gravitons, you have branes, and then branes, if you have many of them, they can back react and change the geometry while leaving the asymptotics the same. So you have geometries, whole deformations of this geometry, and all these things are happening in AdS 5 cross S5, and all that should emerge somehow from UN gauge theory on R31. So how can that happen? We want to understand basically how it works, and we know some of the ingredients that make it work. We have the same symmetries, for example PSU224, which contains the conformal group, and SO6, which is shared on both sides. Other aspects that are kind of make it plausible are, for example, you have 6 scalar matrices adjoint of the UN gauge group, which are fields in the gauge theory, and you can kind of think of them, and it's useful to think of them in many ways as a matrix version of the 5 coordinates of the S5, the 6 coordinates that describe the embedding of the S5 in R6. So these are some of the basic ingredients, but what else? What makes this plausible, or what makes it work? So of course having PSU224 on both sides is not enough. You're going to have a Hilbert space on both sides. You want to match them. And when PSU224 acts on this big Hilbert space, the representations of PSU224 will appear with huge multiplicities. So you have, for example, on the gauge theory side, you have gauge invariant operators which correspond to quantum states by the operator state correspondence. And these states form irreps of PSU224, but they are large multiplicities, and one wants to organize them in some way so that you can match both sides. So there is a combinatorics of these multiplicities of irreps, which comes from many different kinds of gauge invariant things you can build. And also among the generators of PSU224, you have the dilatation operator, and you want to match the eigenstates and eigenvalues of that. Okay, so aside from PSU224, so we may say that PSU224 plus this combinatoric somehow will allow this geometry to emerge. But can we say a bit more about what sort of combinatorics allows this emergence to happen? So it turns out that there is a rather nice symmetry hidden in this combinatorics, and it's the most basic symmetry you could think of. The symmetric group on n objects, which is made of n factorial rearrangements of n objects. These form a group. Now once you have a group, you have the whole representational theory of the group, involving, in the case of symmetric groups, Young diagrams, characters, matrix elements, and all that. And another very important thing that is relevant is that within the world of symmetric groups, there is a duality between symmetric groups and unitary groups, which is called Schur-Weil duality, which kind of plays a very important role in kind of organizing all the combinatorics we have. So the general thing I want to get across is that aside from PSU224, there is a hidden combinatorics, and there are symmetry principles in there which allow this emergence to happen. And they involve the symmetric group and Schur-Weil duality in an important way. So I want to review some of these themes in the half BPS case. So I talked about representations of PSU224, sort of the simplest, nicest ones are the ultra short representations. So I'm going to review them. They include the multiplets of gravitons, ordinary gravitons, and giant gravitons, which are actually branes, but which also provide half BPS states. And this whole discussion will be finite n. It's not a planar discussion because to understand giant gravitons properly, we need to think about finite n cutoffs, which sometimes are described as stringy exclusion principle. And then so I'll maybe spend 15 minutes or 20 minutes on this and then go on to excitations of these half BPS branes, which again can be either themselves half BPS or quarter BPS or non-BPS. And you distinguish between these different ones by looking at the one-loop dilatation operator. So we will be interested in the one-loop dilatation operator acting on perturbations of these half BPS states. And what I want to explain is how symmetric groups and Chauvel duality solve this problem of looking at the one-loop dilatation operator on these excitations. Right, so the half BPS case, we have these ultra short multiplets. Half of the Qs annihilate some lowest weight states, and then the remaining Qs generate the higher energy states. These include Kaluza-Klein gravitons. So you're doing gravity in 10 dimensions. You can Kaluza-Klein reduce on the S5, organize your states in terms of representations of SO6, and the spectrum of states you get will form many different representations of PSU224, and we want to organize that. So we want to count them, and then we want to calculate their correlators, which will give us interactions. So what are these numbers? How many half BPS do we have? So if you fix the number n, which is giving us the energy of the lowest weight. So the representation is an infinite dimensional representation, but the lowest weight has energy n, which could be 1, 2, 3, and so on. So how many states do we have? Here is a sequence. That's the answer. Maybe you recognize it. It's the number of partitions of n. So how many ways of writing 2 as a sum of integers? 2 is 2, or 2 is 1 plus 1, and so on. So partitions of n. And this pattern holds up to some cutoff related to n. And beyond that, it's no longer just partitions of n. Rather, it's number of partitions of n with no more than capital N parts. Okay. So this is roughly what is called the stringy exclusion principle, that this sequence changes. Yeah.
Can you just, if you go back, you say for lowest weight having energy, what the weight of what?
So the energy, the weight is energy. So the
weight
lowest,
of the
yeah,
Oh,
scaling dimension or
I
energy.
see. So that's the, I see. That's the weight of the conformal group.
Yeah,
I see.
that's right. So I'll show you more explicitly what these look like in the gauge theory, and you'll see. Things will become a bit clearer. So half BPS means that the energy or dimension, conformal dimension, is related to a global charge. So out of the Lij's of SO6, we can pick L56. So E equals L56. That is the BPS condition. So how do we build such things in the gauge theory? We can take X5 plus I X6, which is something that has unit charge under this U1 global, and it also has dimension 1. And so for half BPS operators, this is not going to be corrected. So this is an exact equation that holds in the free theory, free Yang-Mills, as well as the interacting theory. So what n equals 1, we want them to be gauge invariant states, trace z, or n equals 2, you can have trace z square, or trace z the whole square, and so on. So you see, why did we get partitions is because if you have two z's, you can put them all in one trace, or you can put them in single traces. So this is 2 equals 2, this is 2 equals 1 plus 1, one trace and another trace, and so on. Okay, so this structure of single traces and then products, how do we see that on the gravity side? Well, the single traces are single gravitons with some angular momentum k, and at least the first approximation, that's a good way to think about it. trace Z to the k are single gravitons, and products of traces are multi-gravitons. So at least the counting of states matches on both sides. So what happens at finite n is that this kind of distinction between single and multi-traces doesn't work anymore. You have identities because it's an n by n matrix. Trace Z to the n plus 1 is trace Z to the n times trace Z plus dot dot dot. For example, if n equals 1, trace Z is just Z, and Z square is Z times Z. So you can't distinguish traces and multi-traces when the powers are comparable to n. So clearly this Kaluza-Klein picture of gravitons should break down at n equals n, but in fact it breaks down much lower. So this breakdown is kind of called the stringy exclusion principle, but this Kaluza-Klein picture breaks down for energies much lower than n, because for energies much lower than n, in fact the energy of your excitation is comparable to the Planck scale, that kind of thing. So this is no longer, the Kaluza-Klein graviton picture is no longer valid. One way to see that from the gauge theory is where does this breakdown happen? You look at the correlators. So this is a multi-trace. So this wants to be a 2-graviton state. You would like it to be orthogonal to a 1-graviton state if this picture is going to hold. And you calculate this this 2-point function if you like. I'm going to drop all space-time dependence. There's an x here and there's a y there. There's some standard x minus y dependence here, which I'm going to drop. What is the combinatoric factor here? It's j1, j2, j3 over n. So if the j's are comparable to n to the 1/3, this becomes order 1. So you can't think of this as orthogonal to this anymore. So much before j order n, the Kaluza-Klein picture breaks down. And we are kind of familiar with this. We know that for j order root n, we should be thinking about BMN backgrounds, which are related to trace Z to the j. And of particular interest to me is j over order n, and how do we organize representation operators there. So you see, so there was this orthogonality that is breaking down between multi-traces and single traces. So how do we build a kind of basis for all these operators, which is actually orthogonal? And it turns out it is possible to build such a basis, which is exactly orthogonal at finite n. And these basis elements are parameterized by Young diagrams. So for each Young diagram, which I'm going to call R, there is an operator, a half BPS operator, which I'm going to call chi R of Z. Now, so Young diagrams come up in representation theory of UN. They also come up in representation theory of S little n. So if I have exactly little n boxes, then that corresponds to a representation of Sn. And if I consider all Young diagrams with little n boxes, that's all representation of Sn. So Sn. So there are two n's. I just want to be clear about that. So all Young diagrams with n boxes. And UN, all Young diagrams, any number of boxes, but no more than n rows. So in the UN theory, we look at all Young diagrams with no more than n rows, and for each of them there is an operator that I'll describe it in a bit more detail soon. And if I just put this constraint that there are no more than n rows, that precisely captures all the finite n relations. You don't need to know any more about how exactly trace Z to the n plus 1 is related to products of traces. All the relations are captured by simply saying that the R's have no more rows than n.
The bulk of these cutoffs are non-perturbative?
Yes, I'll tell you what they are in a minute. Well, it turns out they're bounds on the sizes of giant gravitons. Right. So what exactly are these Young diagram operators? How, given a Young diagram, I give you an operator? So, well, we know that operators are essentially traces or multi-traces. So let's just look at this product of traces, which is just a Z contracted, upper and lower contracted, upper and lower contracted. Trace Z square is this contracted with that contracted with that. So if you look at the indices here, all the indices run from 1 to n because these are n by n matrices. These indices are precisely the same as these indices, and these are a permutation of these indices. So that's the first place permutations appear, and we see why they organize multi-trace operators. So in fact, it is true that any multi-trace operator that involves n z's, it's gauge invariant. So the upper, so this is I1, I2 up to In, gauge invariant, so all indices are contracted. So the lower indices must be some permutation of the upper indices. And in fact, a nice way to think about it is that, so Z is a matrix, and we can think of it as a map from an n-dimensional space to an n-dimensional space. So this n-dimensional space could have a basis. So this is Zji. Matrix elements are matrix elements of this operator. And when we look at V tensor n, we can have ei1, I2 up to ein. And we have in that space the operator Z tensor Z tensor Z tensor Z. And also in that space we have an action of permutations. So for example, if I have the V tensor square, I have the 1, 2 permutation, and it acts on this thing by just permuting it. Whatever is in the second puts it in the first. And I can calculate its matrix elements. And if I do that here, I'll get delta J1 I2, J2 I1. So these are very concrete operators in tensor space, which we can calculate the matrix elements in terms of deltas. So this is one operator, this is another operator. You compose them, you take a trace. That's what a multi-trace operator is. So that's the multi-trace operator, parameterized by a permutation. Now you just sum over all permutations weighted by the character of that permutation in some representation R. Now you get something labeled not by permutations but by representations. So that's the Young diagram operator. So it's some linear combination of multi-traces. For example, if you have the symmetric with two boxes, it's that particular plus combination, and the symmetric is that minus combination. So what is so great about this basis? As I said, it provides a precise counting in agreement with the exclusion principle. It's orthogonal in the free field limit. You do the Wick contractions, and two operators will be 0 if the Young diagrams are different. And there's a kind of simple group theoretic factor you can calculate. And further, the 3-point functions are very nice objects. If I take chi R1, chi R2, chi R3 dagger, it's a number R1, R2, R3 times the normalization depends on R3. And this number is something that has a very nice combinatoric interpretation. It's about how many ways you can get R3 by putting together, there are some rules for putting together Young tableaus. So you take this Young diagram, I should say Young diagrams, take this Young diagram, put it together with this Young diagram by some specified rules called the Littlewood-Richardson rules, and you calculate a number, how many times are you getting this one. That number appears in the 3-point function. So this is a very kind of nice way to calculate all 3-point functions in the half BPS sector. And the other nice thing is that they provide duals to giant gravitons. And also, if you remember a little bit of matrix model stuff, these Young diagram operators are related to, that let's say one matrix model, which is basically what's going on here, is related to free fermions. So these Young diagram operators are directly related to free fermion wave functions, and these in turn are related to LLM geometries, which are geometries, LLM geometries, which are geometries that you get when you let the branes back react. So I will describe the dictionary a bit more detail in a minute, but when you let these giant gravitons back react, you get deformed geometries, and there is a connection between them and free fermions.
Yeah, so suppose I wanted to calculate 3-point functions of these Young diagram operators.
Yes. Right.
If I wanted to calculate 3-point functions of chiral primaries, I just turn on appropriate sources
Mm-hmm.
and do some Witten diagram computation.
That's right.
But your Young diagram operators are admixtures of single trace and multi-trace.
That's correct, yes.
So are you envisaging that there's a prescription for computing Witten diagrams for these chi's, or should I just expand out the chi's and then,
Yeah, I think whatever you in the sector where the R's are order 1,
yeah,
then everything from Witten diagrams, you would apply it to traces and take combinations. That's how I would think about it.
But if I wanted multi-traces, I would have to use funny boundary conditions to turn on sources for multi-traces.
Okay.
Right. So is that what you're imagining, or is there is there a prescription do you think for turning on sources directly in the field theory for chi's?
I don't have too much to say really about the bulk calculation of these things. We can discuss that. I mean, yeah, it's not. Yeah, I don't really have much to say about that exactly.
Geometrically, you're thinking of them as just somehow these giant gravitons, or?
Oh, sorry. So there are giant graviton branes, and then when the operators are order n, little n is order capital N. When little n is called order capital N square, then the LLM geometries, which are back reactions of the giant gravitons. So what exactly are these giant gravitons? So here's a fact about S5. You can think of S5 as an S3 fibered over a disk, and the size of the S3 depends on where you are on the disk. And you can imagine a brane wrapping one of these S3s and rotating around a circle in the disk. And there are solutions like that which are half BPS. So if I'm interested in all half BPS operators, I should be looking at branes like that as well. Interesting fact about them is that as the angular momentum increases, these giant gravitons, the size increases. And in S5, there's an upper bound on the size of this S3. So the angular momentum cannot increase beyond a certain size, beyond a certain value n. So if we're going to come up with a dual state, a natural candidate is that, and there are many ways to argue and then test this proposal, is that these kinds of states are going to be dual to Young diagrams, which are these vertical things. And obviously from group theory, if we're doing UN, there's going to be a cutoff at L equals n, because you're anti-symmetrizing n things, so you will not get anything more than L equals n. And along these lines, the natural proposal is that for multiple giant gravitons, let's say you have many of these giants with different angular momenta, you'll have correspondingly a multi-column Young diagram. So in the sector where you have order 1 columns, all of them large, comparable to n, let's say, then the natural way to think about these states is in terms of branes. There is also what are called dual giant gravitons, where the S3 is large not in the S5 but in the AdS5. They are rotating in the same circle of the S5, so they have the same charges, but they are different operator because they are different kind of brane. So gauge theory naturally offers you a candidate for them, because this, instead of having long columns, you can have long rows, and from group theory there is no cutoff here, and the size can grow as much as it likes with angular momentum. And the candidate dual for multiple dual giants is multiple long rows, and so this picture has been tested in many different ways, and I won't really get into that here. What I'm interested in is excitation. In fact, one of the ways to test this picture is if this picture is right and I have multiple branes, there should be some way of counting the different numbers of strings connecting branes. So what can I say about the excitations of the brane? Now suppose, so here I chose the 5-6 plane. Now suppose I add some excitation that has angular momentum in the 3-4 plane or the 1-2 plane. What are the gauge theory things that I can do? I can add some matrices Y made out of 3-4, let's say, which has angular momentum in this other plane. So people have come up with ways of kind of deforming this Young diagram operator and putting these impurities and finding these excited states of these giant gravitons. So that's the main point of this talk, is to talk about these excited states. And the first thing I'll talk about is what happens to the Young diagram basis when you go to these multi-matrix operators. So to perturb the Young diagram, I want to put some Z's and then some bunches of Y's. So how do I nicely classify in a way that takes care of all finite end relations, that gives me an orthogonal basis in free field theory? How do we do that? There are things called restricted Schur operators. The reason for this name is that this chi r of z's that I wrote before, there are some polynomials in the eigenvalues. These are called Schur polynomials. And now we have z's and y's. They are going to be labeled not by one Young diagram, but multiple Young diagrams, and with some additional group theory labels, which I'll tell you about in a minute. And these are called restricted Schur operators. So what are these operators? I'll tell you what they are. And then if you think about multiple branes, then here is a spherical brane, here's another one. You can think about a string attached to it, or you can have a string attached across. But for example, this is an inconsistent configuration, because the gauge field, the brane carries a gauge field, a U1 gauge field. The string endpoint is charged under that U1 gauge field. So for example, this would be a consistent configuration where I have this and that, but the other one wouldn't be. So there's a counting of different string states, which in fact you can map to a graph counting. So each brane can be represented by a node in a graph, and the strings can be denoted by oriented arrows. And there's a counting of what are the possible configurations consistent with Gauss law, right? And this counting can itself be done using permutations. And I'll tell you how that's done. And then we'll talk about how this counting of string configurations agrees with the counting of operators that you can build which perturb the half BPS operator. And it turns out that the way this works is it involves permutations. And in fact, in the group theory of permutations, you can think about groups, cosets, double cosets. And what shows up in this graph counting is double cosets. And then it turns out that these functions on the double cosets provide some nice simplification of the one loop dilatation operator. So that's where I am heading. Any questions at this stage on the background of the plan? Okay.
When you talked about the multiple branes, the ground state itself, in the S5 they were kind of symmetrized, whereas in the AdS pi they were anti-symmetrized, roughly speaking. I mean, because you put together rows or you put together columns. Is there a...
So I wouldn't really interpret the brane as symmetrized.
I mean, also...
I mean, it's like the z's that are being... the indices of the z's that are being symmetrized, and all are gauge invariant operators. So I'm not really interpreting the symmetrization as a sort of a property of the branes, as a statistics of the branes, not really. But it's just kind of answering the question of what's the dual of that. And I'm just using the Young diagram as a...
So that doesn't have any significance per se?
No, not directly as far as I know. Only indirectly in terms of the cutoffs, because the anti-symmetrized one can't be bigger than something. Yeah.
But suppose I give you a Young diagram with, say, order n boxes.
Yes.
That would be some giant graviton.
Well, okay, if you give me a general Young diagram of order n boxes, I wouldn't necessarily know what it is.
But I mean, we can try to give it interpretations by sort of saying, like look at it in terms of
You could.
And gravitons sort of spinning on the S.
Yeah.
Localized brane wrapping S3 and S5. If I look at it in terms of rows, I can
Yeah.
look at it in terms of
So just for the purposes of counting them, that's a perfectly fine thing. But if you want to study the physics of excitations and so on, that will be, I think, the only reliable regime where you can talk about the sphere giants is a few long rows or a few long columns for S5 giants and a few, yeah. And in fact, in dealing with the one loop dilatation operator, we will restrict attention to a few long rows, few long columns, and so on. Right, so how do we build these multi-matrix operators now? So you have a bunch of y's, let's say m order 1 and n order capital N. So the z's are like the background giant graviton, and then there are some impurities. So you have a whole bunch of indices, m plus n, and then it's gauge invariant, so the lower indices must be some permutation of the all the m plus n objects. That means the permutation must live in S m plus n. That's the symmetric group of permutations of all m plus n objects. Now, but it's interesting to think about when do two permutations give the same operator, because there is no one-to-one correspondence between the operators and the permutations, because the number of permutations is very simple, it's m plus n factorial. The number of operators is a bit more non-trivial, and that's because some permutations give rise to the same gauge invariant operator, and that happens if you conjugate this sigma, gamma, sigma, gamma inverse, because if you put gamma, sigma, gamma inverse, by cyclicity you can put the gamma inverse there, that amounts to permuting the y's and the z's, and if that permutation lies within the y's, Sm, or within the z's, Sn, it leaves the operator the same. So conjugating by this subgroup of Sm plus n leaves the permutation, leaves the operator the same. So, well, that just tells us that in order to think about the operators, we should think about the group theory of Sm plus n, and representations of that are related to representation Young diagram R with m plus n boxes. And we should think about breaking that symmetry Sm plus n to Sm cross Sn, and what are representations of that subgroup described by in terms of a pair of Young diagrams with m and n boxes respectively. Now, given a group and a subgroup, and given representations of the group and the subgroup, you can ask, so suppose I have representation R and I have a state, well, general state will be some state label and the representation. Suppose I wanted to look at the space of states in terms of the subgroup. So basically the representation R can be decomposed as in terms of the subgroup. It will no longer be irreducible. It will be some representation labeled by irreducibles of the subgroup, but with some multiplicities. That multiplicity, I'm going to call it GRSR. I call it GRSR, the same symbol you've seen before, because it's actually the Littlewood-Richardson coefficient, the same one that I talked about before in the context of 3-point functions. Okay, so you have these multiplicities. So once you have multiplicities, what can you do in group theory? So by the way, this is an example of counting to construction. So multiplicities are just numbers, but what can you do in representation theory? You have a basis. What you can do is expand that basis in terms of R and S, representations of the subgroup, states in that subgroup, and then some multiplicity label mu, and then you just introduce a bra with the same, a ket with the same things. So you have something like that, which is a natural thing to do in group theory. You have a state described in terms of the big symmetry. Now you describe it in terms of the small symmetry, the broken symmetry. So you have representation of broken symmetry, representation of small symmetry, state label, and multiplicity label. And if you sum over all these things, you get just the identity operator, which tells you how the state can be expanded in terms of this using some sort of restriction some kind of overlap for restricting the big group to the small group. Yeah.
I can use white chalk.
Yeah.
It's
Okay. Thanks. Yeah. Yeah.
not super clear, just in future.
Yeah. Okay. Well, so this projection operator basically is what I've written here, except for one difference, which is that this mu is not the same as this nu. So now I have a projector-like operator which depends on the rep of the big group, the rep of the small group, the state labels of the small group are being summed. That's why I get something which is Sm cross Sn invariant. But I also have these multiplicity labels, which is how many times this rep Rs of the subgroup appears in the rep R of the big group when I decompose. So this gives me a projector which is associated with this decomposition, and it's a projector, it's an operator in the space R. If I take a trace of that projector along with a permutation, I get what is called a restricted character. It's a trace, so it's like a character. It has this projection type operator, so having to do with restriction, that's why it's called a restricted character. You sum this restricted character with these operators I introduced before. You sum over all permutations is Sm plus n. You get an operator called the restricted Schuh operator, which is labeled by these indices. And they have the same nice properties in the free field theory as the Schuh polynomials. They are orthogonal in the free field inner product. However, unlike the half BPS case, these operators in general are not half BPS. They could be quarter or non-BPS, and their one loop anomalous dimensions doesn't have to be 0. So to get the full physics of these operators, we need to look at the one loop dilatation operator in the first place.
Is that quarter or non-BPS?
That's right.
Are there also 1/8, 1/16?
You could have all that, but if I'm looking at the sector of Z's and Y's alone,
Okay.
then you have half, quarter, and yeah.
So what do you have to do to consider 1/16, for example?
Then you would include derivatives of Z's and F mu nu's and stuff like that. So we had this representation R of the Sm plus n, this representation Rs of Sm cross Sn, the multiplicity index for how many times this appears here. And that multiplicity is the Littlewood-Richardson coefficient. So, and I think this is a good time to pause and say a little bit more about this, because so we said that, you know, Young diagrams, for example, this could be represent a Young diagram of UN as long as n is bigger than 2, but it's also a representation of S3 because it has 3 boxes. Now there is something that we do in group theory of UN, which is, for example, I take this kind of mixed symmetry representation and I tensor it with another one, which is just a fundamental. There is a rule for tensoring it, which is that you can put the boxes of this Young diagram along with that. You can put it here, or you can put it there, or you can put it there. And this gives you, here's a UN representation, the tensor product. What are the UN representations that appear? This, this, and that. But the same combinatorics has an interpretation in the world of symmetric groups. What it is saying, so these are all representations of S4. So for example, I could take that one. Suppose I want to take that representation of S4 and decompose it under the subgroup S3 cross S1. And here's one representation of S3, here's another of S1. How many times does that appear? That number is precisely what's given by this combinatorics here. So in this case, it will be 1. If this and this can be combined to give this with multiplicity 1, then that reduction So it's kind of a duality. Tensoring UN, tensor UN into other UNs is the same as restricting Sm plus n cross Sn. So this is to say, therefore, that if we want to work with these projectors that describe these restricted Schur operators, it has largely to do with kind of combinatorics of putting Young diagrams together. Okay, so if I have some Young diagrams in my labeling before, so if I showed how to put together one Young diagram, this will be in my application, this is little r. So I put together one, I can put another one as well and build Young diagrams with some additional boxes here. So this big Young diagram that we are building, this in my labeling of operators is capital R with m plus n boxes. So here I have drawn an example where capital R is this big Young diagram related to AdS giants. And I'm going to build these restricted Schur operators by sort of the converse process is to take the big Young diagram and remove boxes, because just as here I put boxes in to build a bigger Young diagram, conversely I can remove boxes. So suppose I remove boxes 2 here, 1 here and 1 here, just as a very concrete example. What's the string theory interpretation of that, of these numbers? So rather remarkably, this paper in 2004 made a clear conjecture that if you remove Young diagram boxes from a Young diagram and you ask what's the string theory interpretation of that, well, they proposed that this has to do, those numbers 2, 1 and 1 have to do with looking at, because we have 3 rows, that has to do with 3 giants, 3 branes. So that should have to do, according to this conjecture, with string configurations where there are 2 incoming and, well, let's say 2 outgoing and 2 incoming. And because there's only 1 in this box, it has to do with 1 outgoing and 1 incoming, 1 outgoing and 1 incoming. Sorry. Thank you. So yeah. Right. So if I kind of connect up this picture to give me strings consistent with Gauss law and all possible strings of this form, that counting of strings should agree with the number of restricted Schur operators I can build, where R has this kind of shape, little r has this kind of shape, which differs from big R by these removals of boxes. So it's very clear conjecture. Actually, in the initial paper in 2004, they were mostly concerned with introducing not just a single y there, but introducing y to the m, z, y to the m prime, some complicated string. And in this more recent paper, they explored kind of that picture in the case of just single bit strings. And then you can do things much more analytically and get a bit further. So in any case, the Gauss law will give a prediction for how many such consistent string configurations we can have. And from group theory, we can count how many of these restricted Schur operators we can have. And these two should match. And the general proof of that was not given before, which is one of the things we did. What was known before, very recently, was how the one-loop dilatation operator acts on this kind of sector of long operators. So there were some very nice things known, which is that if you act on these kinds of operators, one-loop dilatation operator, first of all, there are important simplifications. If these are long, so they are semi-classical branes of order n, angular momenta order n, but also you have to make sure for the simplifications to happen that these differences between here and this difference between here and here, these are also large. So they grow with n. They could be order root n, something like that. They have to be large. That leads to some nice simplifications of the one loop dilatation operator acting on this set of states. It forms a closed set under the action of the one loop dilatation operator. And it was also found that if you look at the action of the one loop dilatation operator, there's a nice spectrum. Essentially, you can reduce the problem to harmonic oscillators, which, having sort of a very vivid way to think about it, has to do with sort of the strings connecting these different branes and oscillating. So there are sort of harmonic oscillator systems having to do with the strings connected to the branes. And in arriving at this structure of the one loop dilatation operator acting on this long thing, there was kind of a non-trivial mixing problem that in the past was solved numerically, having to do with which of these S mu nu labels, how do they combine to form nice eigenstates of the one loop dilatation operator. So let's remember the restricted shoe is labeled by one representation of S m plus n, one of Sn, one of Sm, and the multiplicity, which has to do with how these reps appear in decompositions of that. So there was a non-trivial mixing having to do with this S mu nu label related to the impurities. So what we have found in this recent paper is that this mixing problem has a very elegant solution in terms of graphs and double cosets of permutation groups. So I'll just outline that briefly. So the counting of these string brane problems is a question in graph theory. And the next thing is that this graph theory problem is a question in permutations. So for example, let me just draw a simpler version of that picture. Suppose I have a configuration where one string goes round and comes back, another goes round and comes back. Let me draw it as one going out and coming back, and let me draw it as follows. So we just imagine this upper rung as identified with the lower rung. This is another way of drawing this. Yeah? So this is the same as that, so it just comes back. And if I have another configuration that's the same as this, and again I can identify, but in order to get this picture, I must permute the strings first and then identify. Then this strings comes from here, goes here, and then just gets identified, so it comes here, so that's that, and then the other one. So different possible graphs can be related to just different choices of permutation, sigma. And there are m strings, so there will be sigma in Sm. So while we know as before, once you parameterize things in terms of permutations, not all of the permutations give you inequivalent physical objects. And so we have to take into account some redundancy. Which permutations give rise to the same graph? This is just a slightly different picture where a more complicated graph, and again I'm going to identify this with that. So for example, this represents a string going from the brane to itself, and this whole structure is represented here, but that whole structure is represented in a permutation. 1 goes to 1, 2 goes to this one, and so on. But there are some redundancies. So how do we describe these redundancies? Not all permutations give rise to the same, not all distinct permutations give rise to distinct graphs. So if you look at the picture, maybe you can guess what is the redundancy. So it turns out that these was sort of M1, 3 strings coming out of the same dot. It doesn't really matter whether I draw 2, 3 or 3, 2. So there's an S3 symmetry, there's an S2 symmetry and an S2 symmetry for the outgoing strings, and an S3 cross S2 cross S2 for the ingoing. So if you think through all the details of that, which we won't do in detail here, but to take into account the redundancy, what you have to do is take Sm, which is a permutation of all these strings, and then you mod out by, you look at equivalence classes, so permutations which are related. So if sigma is the same, if sigma prime is sigma times gamma 1, gamma 2, where gamma 1 and gamma 2 are in this subgroup, then these two permutations, sigma prime and sigma, actually represent the same graph. So that there's a very simple way to take into account the redundancies. There's a double coset, and you can count how many ways there are, how many points there are in this double coset. So the double coset is a discrete geometry, how many points in it. It is a nice answer in terms of group theory. You take representations of the big group SM. You ask how many times does the trivial one-dimensional rep of the subgroup appear. That's an integer. You sum the squares of those, you get the number of points in the double coset. So this counting of double coset points came from the graph theory of counting strings between branes. So one can actually show that that number of points in the double coset is the same as the number of restricted shores with the shape that I have specified, where big R is this thing, little r is the one where you ignore the y boxes, and that specifies big R and small r, and you let S be anything it likes, and you sum over this to the square of these. That gives you the relevant number of restricted shoe operators you can build. And it turns out that this number having to do with restricted shores is the same as this number having to do with counting graphs. So and the proof of that I won't say much about, but again it turns out that the proof of that involves again this shoe-while duality, which is the relations between the world of unitary groups and the world of symmetric groups. And how do unitary groups come into the game? In this particular case, they come into the game because if you start labeling these impurities, you call them 1, 2, 3, 4, and you look at all possible consistent labelings. Consistent means it arises from this sequence of operations put in one box at a time. That gives you a set of consistent labelings. So it turns out you can relate these labelings to a very nice space, which is VP tensor M. And this is how it's done. Suppose you have a labeling like this, where the number 1 appears in the first row. Then you put, for the first vector here, you put 1, 0, 0. The number 2 also appears. So the second vector, you put 1, 0, 0. The number 3 appears in the second row, so you put 0, 1, 0. So this kind of organizing the different ways you can put these numbers in these boxes has to do with kind of a p-dimensional vector, where p is the number of rows, tensored m times, where m is the number of integers you are putting in. And once you have VP, you can use some facts about UP representation theory, and that's basically what proves that identity that we needed. And that identity basically had to do with the number of points on a double coset. But now again we have the theme of once you can count something, maybe you should do some natural group theory stuff related to that counting. For example, you can count, simplest example is you can count how many elements there are in Sn, sigmas in Sn, there are n factorial of them. So how do I get n factorial? There's another way to get n factorial by, instead of counting the elements of the group, you count sort of dual things to that. And representation theory gives you dual things. So you look at all irreducible representations and fix a matrix element, ij. And if you count how many possible things like that there are sum over dr square. Because I and j run over the dimension of R, and there's an identity, which is that this is n factorial in group theory. Sum of dimension squares of reps is the size of the group. And there is this kind of identity is not accidental. It means there's a one-to-one pairing between group elements and these matrix elements. And the pairing is just you take that group element and you ask, what is the number I get if I take this particular matrix element in that representation? So these matrix elements of symmetric groups give you a natural complete set of functions on the symmetric group. These are functions because if I give you an E-rep and I tell you look at the 1, 1 matrix element, then you give me a group element, I'll get a number. So there is a pairing between, this is basically Fourier transform on the finite group. So now you can apply the idea of Fourier transform not on the group but on the double coset. And there is a way to do that. You have these matrix elements and then you have the reduction coefficients. So if I have a state, the state J in the representation S of the group, how do I expand it into the subgroup? And in particular, how does the trivial rep of the subgroup, how is it expressed in terms of these states? So that gives some kind of reduction coefficients. So you put these things in, you get a number which depends on the permutation along with these representation theory data. But remember, the permutation was characterizing the string, which is a physical thing. So you take that, so now it's natural to look at operators parameterized by that permutation. So you take this coefficient which overlaps these permutations describing the physical string configuration with this complicated group theory data giving the different operators, and then you just look at the one loop dilatation operator on it. It turns out that is diagonal in the string basis. So this one loop dilatation operator on O sigma gives you back O sigma. There is no O sigma prime, there is no sigma sigma prime mixing. It's diagonal in this string basis. But there is also this additional label, the whole box, the R, and so there's some operator acting on that. And it turns out that this delta acting on that was understood before. It has some nice kind of discrete lattice derivative sort of structure, and you go to a continuum limit, it's related to harmonic oscillator type operators. So basically it can be solved, this delta, but what the main point here was that you look at the double cosets which count strings, you look at functions on the double coset which come from representation theory, that gives an ansatz for resolving the mixing, and that ansatz gives you an operator, and this label which measures which string configuration I have is not mixed by the one loop dilatation operator. And that's what we expect, that the physical string is an eigenstate of the one loop dilatation operator. Okay, so I'm going to conclude. So just a summary, symmetric groups, their representation theory, in particular as applied to double cosets, have provided an ansatz for diagonalizing the one loop dilatation operator in a sector of excited giant gravitons. And more generally, this is part of a bigger lesson that symmetric groups often seem to play a big role in how strings and branes emerge from gauge theory. And this is a lesson that has been seen in much simpler models like two-dimensional Yang-Mills, but it continues to be true. You might have thought it's only a particular feature of very kind of simplified models, but the role that symmetric groups, and in particular this Schur-Weil duality, the connection between the world of symmetric groups and unitary groups, continues to play a role in this broader AdS CFT. And I think basically this has to do with the fact that you have PSU224 on both sides, but there are huge multiplicities of the E-reps of PSU224, and what's the structure that organizes that? It's the symmetric group and its associated representation theory and its associated dualities. And in particular, this is a nice example where we really see how these tools of representation theory provide you the tools for stepping from the counting to the construction of states, of D-branes and their excitations. I'll stop here.
Question?
So if symmetric groups are somehow fundamental in the story, then 1/16 PPS states which are not of the form you've considered must also somehow appear, do you think, must also be described by some variation of this formalism? Or
I think the general lesson should be right, that except the kinds of things you will end up doing will be a bit more complicated. For example, here I dealt with just two impurities, X and Y. You have many impurities, you have multiple products of symmetric groups there, so that's one extra complication. But I would say yes, so it's certainly worth exploring how far you can go with permutation groups and their representation theory with these sectors as well.
Following up on that,
Yeah.
so suppose I wanted to describe, let's not even say 116 BPS, just 18 BPS.
Yeah.
So I keep all the three complex scalars,
Mm-hmm.
and can I start thinking of young tableaus built out of colored boxes, and use that kind of representation to talk about a general 18 BPS scale?
That's a very good question. I guess that link hasn't really been, properly made yet. We know a lot about the counting of eighths and from some of your work as well. Basically, it's related to n particles in 3D simple harmonic oscillator. That's one description. So one fact maybe along these lines I should mention is that there is a way to take this system and take the U3 symmetry, so you can organize things according to a representation of U3. And from what I've said, one should expect a Young diagram Y of UN. So it is possible to label all the states in a one-to-one way here using lambda, Y, and some additional labels, which all have some group theory meaning associated with that. And it turns out this comes very nicely from the construction of this system as arising from quantizing giants in S5. So there is a labeling at the level of the states, but translating that into an operator which further should be a null eigenstate of the one-loop dilatation operator, that hasn't really been done yet.
Anyone? Speak again.
Okay, thank you.